Yes, so I'll switch gears with my talk. I'm going to present computational things. So I'm a faculty member at USF in the physics department, and I work in theory and simulations of all sorts of mathematical systems. So today I'm going to present our work on how machine learning models can be used to statistically predict frictional properties of 2D materials. So this is a new model, new approach for me personally. So I'm going to show a lot of basic details to show you how machine learning models look like. It was a really steep learning curve for me personally, because we do DFT, we do linear functions, we do type binding, but we don't do machine learning. So this is a starting point for my group. So the work was supported by, where'd it go? By the Department of Energy, and it was done in collaboration with the, yes. But it works. In collaboration with my postdoc, Ranja, who is already a faculty member in India. So, friction. Okay.
Only for me.
I think I'm pressing the wrong order. Okay, so friction. Everybody knows and experiences friction in everyday life. When we have two objects in proximity and we push one against the other, there's always a resistance. So this is the ubiquitous dissipative process that exists in nature, and we see it every single day. So we distinguish between two regimes of friction. One is the static regime, where I have an object on top of another one, and I start pushing the object on the top, and I push and I push and I push, and at one point, the object starts to move. So this process, until reaching that threshold point for the motion, is called static friction. And as soon as the threshold point is overcome, then we have a kinetic friction motion that happens afterwards. So today, I'm going to talk about static friction models. And tomorrow, we have a totally different talk. Again, the work comes from my group, by my postdoc, now Lee, on the kinetic friction of motion, the dynamic friction. So the models you will see are totally different. One is computational, the other one is analytical. Okay, so even though we experience friction every day, the mechanisms that govern friction until today are not completely clear. Nobody knows exactly what are the factors, what are the mechanisms that govern friction, especially at the nanoscale. One thing is for sure, however, that this is a materials-dependent phenomenon, okay? Depending on the two materials that are put together and they're set into some kind of motion, friction is big, small. We talk about good lubricants, bad lubricants, and so on. So there are many, many experimental studies demonstrating this. They show that chemistry of the contact of the materials in contact, defects and imperfections, surface roughness, adsorbate, intercalate, elasticity, temperature, they all map of the frictional process between two materials. Okay, and now recently, 2D materials emerge as possible candidates of good lubricants. Okay, again, a lot of experimental studies, actually all of them, most of them experimental studies, showing that this is indeed the case, and there's several examples, so several representatives already in this pool: graphene, hexagonal boron nitride, black phosphorus, some transition metal alpha-carbonides. And experiments have shown that even depending on the thickness, maybe you put 1, 2, 3 layers, that affect motion. Strain can be also a factor of engineering. An external field, frictional lubrication process between two 2D materials can be vastly different. And all of these can be used as modulating factors. Okay, but as I said, the phenomena, the mechanisms that really govern friction are not completely understood till today. So what I said, okay, I'm going to go a different route. Rather than asking the question about the mechanism that governs friction, which is asked for the talk tomorrow, I'm going to look at things from a materials perspective. And I'm going to ask, okay, well, how do different materials, okay, how do they behave in the context of static friction? And one thing that people usually consider for static friction is the construction of potential energy surfaces, as here it's done for, let's say, copper 100 surface moving above another one. So from the potential energy surface, we can identify directions where the friction is big or small. And I could say, well, if I'm sliding the materials this way, then I have a good lubricant. If I slide them another way, then I have to overcome a big energy. So these properties now, to construct the potential energy surfaces, we need one property, which is the adhesion energy for different stacking patterns. And this, of course, is accessible via density functional theory. So one potentially could take 2 layers and form different stacking patterns, find the energy, the total energy, and then construct the potential energy surface.
To what extent do you think that inhomogeneities may play a role then? Because you might think in nucleation type. So
sure. Well, DFT is perfect material, so homogeneity, we can't really. So I'm going to come to that point, by the way, in some kind of a general way. So one property that helps us understand static friction is this potential energy surface, which is essentially the adhesion energy at different stacking patterns. But in addition to the adhesion energy, another property also is important for friction, which is the van der Waals energy, which is part of the adhesion energy. And the van der Waals energy, as we know, is important for the interaction, especially for 2D materials that are chemically inert. But in addition to the van der Waals energy, another property that matters for static friction is the corrugation energy. And this is the difference between the energy of the state with the lowest energy minus the one with the highest energy, because the corrugation energy is going to give us a measure of the energy barrier that needs to be overcome to set the material on top, let's say, in motion with respect to the one on the bottom. So from what we did, we said, okay, we're going to focus on these 3 properties: adhesion energy, van der Waals, corrugation energy, and we're going to use this knowledge that we can get from density functional theory to develop statistical models using machine learning. So that's the whole state of the statement of the problem that I'm making. Okay. So one thing I understood about machine learning, at least the machine, from a very basic understanding of the model, the first thing you need is data, right? We cannot do machine learning if we don't have enough data and if we don't have good data. At least that's one of the basic things that I hear everywhere. So I need to collect the data, okay? And of course, the data that I'm discussing, which are the adhesion energy, corrugation, it's not available, okay? It's not available experimentally, maybe for a handful of materials, but not for the many materials that I want to model with machine learning. So for this reason, I need to collect the data. I need to make the data myself. And the best way to do this, the fastest way to do this, is via DFT simulations. So we go to one of the databases that is available. and look at the types of 2D monolayers that are dynamically stable and they are chemically inert, okay, they're non-magnetic. And we went to the C2DB database that now has over 5,000, I believe, monolayers that are predicted. And we picked a certain number of them based on the characteristics that I showed you, and we grouped them in various groups. Okay, I'm going always the wrong way. Oh. Okay. We picked several materials in their monolayers that are positioned now in 9 different symmetry classes. For example, transition metal alkylcalgenides in the 1T and the 2H phase, some Janus materials, also black phosphorus, graphene, silicon, germanium, they're all in here. 9 classes of materials. So for each class of material, okay, and for each member, so each specific monolayer, now we bring another one and make a bilayer and start looking at the different stacking patterns for each symmetry class. Based on the symmetry of the unit cell, we consider different types of stacking patterns. And in essence, they are all variations of AA and AB stacking that we know well from graphene. And here is an example, let's say, some stacking patterns for transition metal alkylcalgenides in the 2H phase. So for each material, for each stacking pattern, we perform basic DFT simulations to collect the data. And in this graph, I'm showing you how the data now is prepared. Because it's not available, I have to prepare it. And we start with 520 dynamically stable monolayers. They're all in these 9 symmetry classes, okay? And from these monolayers, we form bilayers, okay? And we end up with 760 bilayers depending on the stacking pattern. So all of these stacking patterns now are created, and for each material, we perform basic density functional theory simulation, and we find, and we add a van der Waals correction to it, DFTD3 option, that's what we chose. And based on the simulations, now we collect a bunch of data that is now tabulated and available for other people to use. And we call it the bilayer database. So we are able to get the band gap, static dielectric constant, effective mass, charge transfer, spin-orbit coupling, power, feedback coefficient, all of these now properties are available for these bilayer materials in the different stacking patterns. So this is the part of the one part of the problem. Now that the data is generated, the 3 target properties that I'm looking at are the adhesion energy, the van der Waals energy, and the corrugation for each class of materials and the different members. So in here, I am giving you a scattered plot of the adhesion energy for the ground state stacking for each material, the corrugation energy, which is the difference between the 2 stacking patterns with the lowest and highest energy, and finally, the van der Waals energy that is part of the ground state adhesion energy. And this is what it looks like. So from what I could tell, you know, a lot of points now in this small energy window up to from, let's say, from 0.1 to 4 joules per meter squared. But there's also plenty of outliers. And this, I guess, the small energy indicates perhaps that most of the bilayers are actually van der Waals. The interaction is dominated by van der Waals interaction. Okay, so in addition to this point about data, so machine learning, we have to have enough data that is relatively reliable. Well, all of this data now is generated in one tool, so in that sense, I can say it's reliable. Okay, and now the second part of machine learning, we now need to have some kind of descriptors right? So you can do machine learning if there are no descriptors for the particular system. Well, here, what we have done, we have made a list of easily accessible atomic and monolayer features for all materials. So here I'm giving you some examples. For example, part of the modeling will be, I have to consider the boiling point, the specific heat, fusion, ionization energies, radii of atoms, I don't know, some packing fraction, area of unit cells. So properties that these on the top I can get, and we have tabulated them from available data. Let's say international crystallography data, let's say, has this data. And the second part is available from the database, T2DB database, but it's also available from DFT simulations, and they're also tabulated. So I end up with about, let's say, 56 features. So I have 760 bilayers, and I have 56 essentially parameters. Well, with 56 parameters, we can fit anything. Too much. So the first point now of the actual machine learning process is to reduce the number of features. Okay, so this we call feature selection. And for this purpose, we used many types of machine learning models: linear regression, ridge regression, lasso, I don't know, GBR, XGBR. So the goal was to reduce the number of the 56 features to something more reasonable. And from the literature, I see anything that is about 10, 15 features in a data collection that is about 1,000 points is reasonable. So we were able to reduce, let's say, this is maybe 12 features here, 12 here, and 15 here. And so that's the first process of the machine learning model. After the reduction, and of course, so for those who do machine learning, okay, the final set is essentially for linear dependent features with Pearson coefficient less than 0.8. In other words, we're trying to say that these features are not really interdependent. And so that's what this coefficient is supposed to signify. And this is what now the optimization process looks like. Okay, now the machine learning performance is checked against very different combinations of the higher ranked features. And then we look at the mean square ranking of the final selection feature, which essentially tells us how the features of the atoms and the monolayers are prioritized in their effect, in their importance for each property of each of these three properties. And what we see is, so this is, I guess, standard that machine learning models do. We look at the feature optimization with the adhesion energy and for the corrugation energy. And it also gives the Pierce correlation between the input features and also the targeted properties, which are the three energies that I have given. And for example, let me show another one. Okay. And again, for the third property, the same. So obviously, I cannot write packing fraction, area of unit cell, density here. We gave symbols that are also tabulated in the paper. And what we see is, let's say, the packing fraction, the average atomic polarizability, the surface atomic density. They have a strong positive correlation on the adhesion and van der Waals energy. But the unit cell area and the average electronic affinity, they have a strong negative correlation with the adhesion and the van der Waals energy. In other words, if one increases, the other one decreases. And let's say and the larger maximum bond length gives larger correlation. So this is what the graphs tell me. So one conclusion that I can draw, let's say the larger the similarity in the surface atomic melting point correlates with larger energy and vulnerable, but it also correlates with negative correlation energy. So all of these are available in them. So you have to just look and make these conclusions from the model. Okay, so, but now we have to make some kind of model selection and predictability. And what we have done is take all the machine learning models that I showed you earlier, and now we're going to see which one performs the best for each property, which one of these three properties. And this is the scheme that we follow. So we compare the models, we tune the hyperparameters, which are the features of the model, and at the end, for the best performing model, we do sharp analysis. Okay. So this is the scheme that is sort of, I learned that is sort of standard for machine learning model. Okay. So to initiate this, now we take all this data and separate into training set. 90% of the data is training set, and 10% is testing. And this is the distribution. So when I submitted the paper for review, the reviewer said, I want to see the distribution of those that are being trained and those that are being tested, because it may be that you have such a good fit, maybe all of your testing data was in one class. So this shows that it's not in one class, but it's some kind of a random sort of distribution. And it turns out that from all the machine learning models that we tested, the GBR performs the best for the adhesion and the corrugation energy, and XGBR for the van der Waals energy data. Why? I don't know. That I do not know. Okay, so here is the model that you see. This is the prediction model for the adhesion energy. Okay. And to assess the predictability of the model, we do a metric test. So this is the coefficient of determination and the root mean squared error. So the R squared essentially measures how well a model predicts or fits the trained, the predictive data. And we want this value as large as possible. So 0.98, 0.95 is a really good number. And the root mean squared error shows the deviation of the predicted values compared to the actual value. And this we want as small as possible. So this big and small. After, and as you can see, everything now fits on one very close to the line. That means the model is doing relatively well. I don't have a lot of points that are outside of the line. And from the model, we also find how the order of the features, of the atomic features affect. Which one affects the most, which one affects the least, being in an order for this particular problem. So the packing fraction and the average melting point. The average melting point means the melting point of the atoms at the interface are the two features that make the most effect on the adhesion energy. Okay, so we do also see that this is another standard curve for the model, which shows that the residual errors are relatively small, you know. We do the same, okay, for the corrugation energy. And here we have 15 features. Again, the R squared is big. The root mean squared error, it's even smaller. Everything fits sort of on the line, which is the goal. And we see that now the electric constant, the bond length, and the melting point have the highest impact on the corrugation energy. So polarizability and strong bonds that are captured in the bond length and the melting point appear to be most important for the corrugation. And we do the same for the van der Waals energy. I guess the model here is the best, I think, the best performance, because R squared is almost close to 1, and the error is the smallest when we compare it to the other two properties. And again, the 12 features affecting the van der Waals energy now reordered, showing that the packing fraction and the average of the p electron valency and the area are the three properties that affect the van der Waals energy the most. So you can now think about the physical meaning of this. For example, larger packing fraction means larger voids in the structure. That means stronger van der Waals coupling. If you have a smaller unit area, we have larger overlap of one layer above the other, stronger van der Waals energy. And then again, we have larger valency of the average p electrons, then stronger van der Waals energy as well. Okay, now the next standard thing in machine learning model is to look at the so-called SHAP analysis, okay, and the SHAP values. Actually, this is called a Shapley value. Again, it comes from game theory, and the SHAP value gives us a quantitative measure of the importance of each feature of the predicted outputs. And it corresponds to the average marginal contribution for each layer by taking into account all possible combinations. So this is a standard curve, or I don't know, figure, where we show the SHAP value, how it impacts the adhesion energy, okay? And, you know, in addition, I can also now study the correlation between different properties of these 12 features, how they affect the adhesion energy as well. For example, in this curve, we show the correlation between the average melting point of the nearest neighbor's atom in the gap and the layer thickness. So we see that the average, so we did that not just for these two, but for all combinations of the 12 features that are here, and they're reported in the paper. So, for example, this figure tells us that the melting point and the layer thickness are really strongly correlated. Larger melting point corresponds to more material, and the largest SHAP value that we see here corresponds to features that have the strongest effect into the targeted property. So it also correlates with the data that I showed earlier. And then a similar thing that we can see for the SHAP analysis for the van der Waals interaction. Again, a similar curve. And here we show the correlation between the area and the average melting point. So the correlation is inverse. Okay. Then now you ask, well, what about individual materials? So I went into all this database that we created and all these machine learning models, and I want to look now at individual materials. Some of them, yeah. And I picked one. Okay, so this is a Janus material. Okay, and now we show the SHAP values for the bilayer made out of this Janus material, for the adhesion energy, for the corrugation energy, and for van der Waals. So we have the base value, which is calculated based on the average value of the training set. And again, you see that red thing, which corresponds to the largest number for the melting point, indicating that the melting point is also in agreement with the data that I showed before, that is of most importance for the adhesion energy. Okay, and this is, I think, a positive correlation. The red color corresponds to positive, and the blue color corresponds to negative. So then I go to the corrugation energy. Again, we have an average value, which is here, and we have the actual value of the material and all the SHAP values for the 15 now parameters that enter the corrugation energy are shown, and the same for the van der Waals energy. Okay, so this brings me to the end of my talk. I want to emphasize 2 points, right? One is that machine learning requires reliable machine learning models requires data, and the data that is easily achievable to us comes from DFT simulations, and this is what we have done. The model would be much better if we have the same data, but now from experiments, right? So experimental data. I don't think that exists. The other thing that I want to show, to emphasize, is that for machine learning model, we need descriptors. And the descriptors, as you can see, now the descriptors now take into account the physics of the problem. What are the physical properties that affect friction? I don't know what they are in effect, but what I do know is that if I'm going to do a machine learning model, I have access to easily accessible features that are going to help me develop this statistical model. So physics come into play by finding essentially the descriptors that the physical properties somehow that affect this process. And then the rest is that many machine learning models, actually all of them that I've used, are available for free. All you have to do is just use them. One thing that when I received the reviews from one of the reviewers, he said, well, fine, you show this, but what about if you bring new materials? You know, from the database into the database, you have other materials. If you pick others, how does your model compare? You know, does it work? So we took the model and we picked 20 additional materials. I believe it's 15 or 20 from the C2 database, and the model worked very well. Then a natural extension for this type of work is to have multi-output regression. In other words, now I take the 3 properties, and instead of modeling them individually, I model them together as one entity. And we tried, but we didn't have time. Very, very demanding, not so easy. Maybe our descriptors are not good enough. So thank you so much. That's the end of my talk.
We have time for one question.
So it looks like the difficulty here you have is getting actual experimental data. So you have all this DFT data and you can do machine learning. Let's imagine both the algorithms are, everything is fine. Is it possible for the machine learning algorithms to make suggestions of experiments that you could do on a very small sample, and that gives you confidence that everything's good, and then it keeps improving in that way? Not the initial data set from experiments, but the suggested experiments that can then just give you confidence.
So this type of machine learning model, which I assume is the most basic one that you can do, I use that as a stepping stone to learn what machine learning can do for us, cannot make these kind of predictions. It doesn't tell you what experiments you need to do. But from what I know, even higher level machine learning, I don't know if they can tell you exactly what to do in the lab. I'm not sure if that exists.
So how would you know?
No, what?
How, so what is the connection to experiments that's
Well,
telling you that?
Well, I mean, if you're looking at adhesion energy, right? So AFM tips, whatever people do standard, so that's what you do. So you're studying the adhesion energy by layers. So you do 2 graphenes, 2 HBN, 2 TNV, and for each one of them, you do adhesion energy measurement. So this is pretty standard. But I thought you were asking me about novel.
Yeah.
Yeah, so other than that, you know, I'm targeting a property, whatever experiments people use, that's what we're going to start with. But how to design a new experiment, I don't think machine learning can do that. It can only tell you about a new property, but what to do in the lab, we can't substitute that. Yeah.
Lilia, the last talk.